So basically, Luming's been the guy in the group who's been at the forefront of all the nice trends. So we'll have to find someone else to do that once he leaves. All right. With that, I'll let Luming start.
Okay, thanks to Brett for the nice introduction. So, hi everyone. It's my pleasure today to give a presentation entitled Managing Visual Knowledge from Pre-trained Models. So now, I guess let's start it. In the past decade, supervised learning achieves huge success in computer vision across multiple fundamental tasks, including classification, detection, and segmentation. This success is even not limited to 2D images only, but also propagated to the field of video, vision language, and 3D. The success is mostly credited to the dominant learning paradigm in deep learning nowadays, that is training large-scale neural networks on ever larger datasets. As a PhD student in computer vision, I felt extremely powerful, and for quite a long time, I believe that we can use this pipeline to solve almost any vision problems. Until one day, a friend of mine who studies biology at Cornell came to me asking for help on using computer vision techniques to automatically detect and count certain type of nematode eggs, which is a kind of parasite, in the macroscopic examinations. I said, no problem, man, you totally got the right guy to ask. So now tell me how much data do you have? And he probably said with the help of the whole lab, we have like 50 images with a notation now. Is that enough for you to do the magic deep learning? And without any surprise, given this very few label data, the existing technique failed catastrophically. So what's causing the gap? It turns out the previous successful story is actually built upon many large-scale datasets and annotations. For example, YouTube 8 million have over 300,000 of hours of videos, and Waymo Open Dataset have over 12 million 3D boxes. However, just like the case I mentioned earlier, for many tasks, we are unable to collect such large datasets. One reason is high-quality data annotation is quite costly. Here are examples of instance segmentation and a video of labeling for self-driving. Each data point will require a long time for a person to label. And even worse, some data is even impossible for cross-sourcing labeling, especially when it requires domain knowledge expertise. For example, medical image, fine-grained species, and 3D modeling. And most importantly, as human, we actually don't need that much of data for each task. For example, we only need a few images to quickly learn how to recognize a new animal category, as shown here. So in summary, my PhD works are trying to tackle these challenging real-world computer vision problems where data is constrained. Intuitively, we think it would be helpful to utilize past visual experience. As human, we definitely are not solving each task totally from scratch. Instead, we are implicitly using the perception ability we obtained from previous visual experience, like the heuristics we use to recognize new category, how to draw correspondences from different images or objects, and what is a realistic image and what is not. And in the context of deep learning, this knowledge is implicitly embedded in the large models that are pre-trained on existing datasets, which is usually large-scale, but might not be well aligned with the target task in terms of training objectives and data distribution. Following this strategy, my PhD works could be divided into two categories: how to build pre-trained models and how to adapt pre-trained models. In the first category, I mainly worked on how to use meta-learning to build better pre-trained models, image representation, such that it can enable future learning. That is, the model can easily generalize to novel classes using only a few labeled images. In the second category, I mainly worked on adapting pre-trained models to enable all kinds of downstream tasks where data is constrained, ranging from recognition to dense prediction, and to 2D and 3D generation. Today, I'm mainly going to talk about the three works in the second groups. For the first part, I will talk about our work in ECCV last year on how to adapt efficiently and effectively adapt a vision transformer on data-constrained downstream tasks. And our method VPT only needs to fine-tune less than 1% of the network parameters to beat other methods. And for the second part, I will talk about our newest work that visual correspondences emerge from image diffusion models without any supervision, including geometric correspondences as on the left, we're matching points of the same object, but from different viewpoints. And semantic correspondences in the middle, we're matching semantic parts of the same category, but for different instances. And temporal correspondences on the right, we're tracking the objects through the whole video. Lastly, I will talk about recent work at SIGGRAPH Viewfield that with only a few reference images, it can input and open the target image with contents that should have been there. For example, recovering the cron of this dancing girl here. Before diving into the main content of today's talk, I'd also like to touch upon each of my other works in just 1 minute each to give you a flavor of what they are like. In this very first project of my PhD, we focused on facial recognition. That is how to design a meta learning model such that it can learn a new image category with very few images. As human, we're actually using post-invariant features to accomplish this task. For example, the color of the beak and the wings to classify these two bird species. We found that simply embedding these heuristics of object parts into the representation would lead to a huge boost, as much as 20 accuracy points to the facial performance. However, this cannot be naively extended to general objects because there doesn't exist a unified set of key points for different categories. Therefore, we designed a new meta learning algorithm to enforce images to automatically find corresponding part via linear regression, then use it to do reconstruction on feature maps. The better the reconstruction quality is, the higher probability that image pairs share the same class membership. And this leads to the state-of-art performance on multiple benchmarks. And beyond recognition, data issue is even worse in the content creation field, where licensed 3D assets are extremely expensive. But our work, Magic 3D, showed that even without any 3D data used for training, we can still generate high-quality 3D models by utilizing the 2D image prior in the pre-trained text-to-image diffusion model. Here are a few NERF results we got, and here are more mesh results. More specifically, we transform it into a test time optimization problem, and we optimize a differentiable 3D representation such that its renderings are realistic images that match the text prompt. And we can also edit the existing 3D model by modifying the text prompt here. For example, changing the material of the bunny and also the thing she is sitting on. Okay, so now let's dive into the first part of the talk, visual prompt tuning. So in the past few years, we all witnessed the rise of so-called foundation models, the large-scale pre-trained vision models that demonstrate strong generalization performance on downstream tasks. For example, CLEAP, Dino, and MAE. All these models are empowered by a scalable neural network architecture called Vision Transformer, or VIT, that demonstrate better performance compared to convolutional neural networks, especially when scaling up. It first split the images into patches and then use self-attention layers to encode embeddings layer by layer. However, just like the example we showed in the beginning of the talk, we still need to adapt the pre-trained VIT to specific downstream tasks due to the gap between pre-training task and target task, including data distribution and training objective, all simply the desire to further boost the performance because we have more downstream data. So the question is how to adapt the VIT effectively and efficiently. The most straightforward approach is to do full fine-tuning, that is, fine-tune the whole backbone and head network for each downstream task. However, this will lead to several issues. First one is overfitting when the downstream data is small. And meanwhile, just like the trends in NLP, the vision model size is still growing, leading to over 22 billion of parameters nowadays. And this would also lead to another problem, that is storage problem for full fine-tuning, because we need to store a full copy of fully fine-tuned parameters for each downstream tasks. For example, 22 billion parameters would lead to over 60 gigabytes if without any compressing. And the other alternative is head tuning, that is freezing the backbone and only train a head network for each downstream task. This is indeed easy and cheap, but the performance is usually suboptimal because there's not so much space for the pre-trained model to adapt, especially when the domain shift between pre-training and target is large. Then the question is there any way to adapt the pre-trained VITs both effectively and efficiently? That comes to our proposed method, visual prompt tuning, where it learns prompt tokens for each downstream task. And prompt tokens are low-dimensional vectors that composing only less than 1% of the whole network parameters. So the fine-tuned model would not be easily overfitted and also lead to efficient storage because for each task, we only need to store those learned vectors instead of the whole backbone parameters. Specifically speaking, given an input image, VIT first split it into patches and embed them into vectors. And here we inject a few extra learnable token vectors. Here we use fire to denote tunable parameters and snowflake for frozen weights. Then the patch embeddings and the added prompt tokens are fed into self-attention layers together. And similarly, we can do the same thing repetitively for each transformer layer and layer by layer. Then the final embedding are fed into a trainable task-specific head network. The whole tunable parameters only consists of 0.3% of the whole network. We call this version VPT deep because we inject the prompts for each layer. And we can actually also do this only for the first layer. And we call this design VPT shallow on the right. And both are extremely simple to implement, only 25 lines in total, as in a third-party implementation. And we conduct experiments on adapting ImageNet pre-trained VIT to 24 different downstream tasks, including both small domain shift like fine-grained visual recognition and large domain shift like 3D shapes, medical or satellite images. And 19 of them are designed to be a data constraint setup containing only 1,000 training images each. And here are the main results, comparing VPT to full fine-tuning and linear probing. We're only tuning, like linear probing means like only tuning the linear head network for each task. And we can see VPT outperforms all the linear baselines and 20 out of 24 tasks versus for fine-tuning, but with much less parameters. For example, here, in order to serve all the 24 tasks, for fine-tuning need to store 24 copies of the weights, but VPT only need to store 1.2 copies of it. And here's a more detailed visualization, including more baselines. The x-axis is tunable parameters in log scale. So left means much less extra storage. The right axis is relative accuracy gain versus for fine-tuning, so higher is better. And each transparent scatter denotes each specific task performance. And we can see that VPT, the red star, go ahead.
Oh, yeah. When you say tasks, do you mean like different data sets? It's like all classification?
Yeah, yes. Like different classification data set. Yeah. And we can see VPT, the red star, like outperforms all the other baselines. And although VTAB1 key is already a pretty good low-shot setup, we also did an evaluation on dataset size on fine-grained visual recognition. As you can see, when having a lot of label data, VPT and for fine-tuning will all get pretty good performance with a large advantage compared to linear probing. But when training data get less and less, for fine-tuning will easily overfit and performance degrades quickly. And VPT demonstrates both for fine-tuning and linear probing across different data sets size. So here the x-axis is a fraction of the downstream training data, and the y-axis is the test accuracy. And here's a visualization of the learned image representation for different tuning methods on V-type tasks. For fine-tuning is on the top right, and VPT deep is on the bottom right. It shows that just like for fine-tuning, VPT deep lead to linearly separable features by using much less updated parameters. We actually have a lot more analysis in the paper, including different VPT design choices ablation on number of prompt tokens, and how to further improve the inference efficiency of VPT. So feel free to check our paper if you are interested. So in summary, VPT demonstrates that learning prompts is an effective and efficient way to adapt the pre-trained VITs to downstream tasks, especially in the data constraint scenario. And our work is also the first one on parameter-efficient tuning in computer vision. And up to now, it's still one of the most highly cited paper in ECCV last year. And follow-up works including enable VPT on more applications beyond classification, including like segmentation, vision language, 3D, and even generation nowadays. And there are also papers trying to understand why VPT works and how to improve it in terms of performance and training memory, including like visual query tuning and neural prompt search. And we really need a large number of prompts for like visual prompts, and also this iClear paper recently. And one interesting thing I want to mention here is we also consider extending visual prompt tuning to visual prompt training, which means that the prompts are learned together with the whole VIT from scratch during pre-training. And recently, a paper called VIT Need Registers got outstanding paper award at iClear and this year, and they are essentially doing such things, and also showing great performance boost and visualizations. So definitely worth a look if you are interested. Okay, I will just pause for a bit if you have any questions. If not, I'll just dive into the second part of the talk, diffusion features.
I had one tiny like detail question, which maybe makes sense to ask in real time here.
Yeah, sure.
So in this thing, so you have this network or this model that has a bunch of transformer layers in it.
Mm-hmm.
And I guess each of those has like some number of inputs that comes in and some number of outputs that goes out.
Yes.
And now you have these additional key or these additional prompt embeddings.
Yes.
Like why is it that like which inputs do these go in? Are those inputs that were originally trained with some of the tokens going in, or why are those inputs there for those?
You mean what exactly are the parameters we're training here? If I understand the question.
I guess so. I guess I think that the thing that's labeled L1 there that's frozen was trained with no knowledge of visual prompt tuning. Right? It was just trained as a model for doing recognition.
Yeah, kind of. But because I would say the matrix projections are fixed, but the key key query and value bank, like vector banks, are being changed because we inject more tokens.
Okay, I see. So you can put, because of the way the architecture is set up, you can feed as many tokens as you want.
Yes, exactly. Yeah.
Okay, gotcha. Thanks.
Cool. So I'll dive into the second part of the talk, diffusion features. And there's an often told story that in Takeya Sapini, who is a famous professor at SMU and also a pioneer in computer vision field, the three most important problems in computer vision are correspondence, correspondence, and correspondence. Indeed, drawing correspondences between images is a fundamental vision problem, and it serves as a building block for many tasks, including like 3D reconstruction, image editing, and video tracking. And this is an easy task for human because although we barely learn with any labels, we can easily match object parts either across viewpoint and lighting changes, all across instances, categories, or even domains. For example, drawing a correspondence of this cat nose here. However, this is much harder for computers. Current methods usually relies on large-scale label data to train the specific neural networks such they can do specific correspondence tasks. Therefore, a natural question arises, like, can computers learn correspondences without label data? And in order to tackle this problem, we seek help from diffusion models, which have superior image generation results. We hypothesize diffusion model seems to capture correspondences implicitly, given the following two observations. The first one is the high resolution details I observed when I was working on Magic 3D, the 3D generation project. To be honest, I'm still amazed and also confused why the whiskers would appear during the nerve optimization process. Because even for 3D reconstruction, registering such fine-grained 3D points or volume would require quite well-aligned static multi-view images and accurate camera poses. However, here, this is simply achieved by just using the skull estimation from the pre-trained diffusion model, which is actually a 2D image model. And the other observation is that diffusion models also enables image translation, such as changing a cat into a dog. Intuitively, in order to perform such editing, the diffusion model must implicitly understand the correspondences between the two objects, such that it can replace the cat nose with the dog one. Then the question is how to retrieve this correspondence knowledge. Let's first look at how diffusion model works. Given the sample input image x0, different magnitudes of Gaussian noise is added to obtain noisy data point xt. Here, t indexes time step, and larger t involves more noise. If we train a neural network that takes xt and t as input and predict the input noise, then starting from a normal distribution, the network can iteratively estimate and remove the noise of xt to get a cleaner data point xt minus 1, eventually leading to a sample x0 from the target data distribution. So given an input image, we propose to extract image features using a pre-trained diffusion model, then use them to do correspondence tasks. Specifically, we first add a certain amount of noise to the input image x0 to get xt. Then feed xt and t into the denoising network, which is essentially a UNet. And we are able to get the intermediate feature maps at certain block I as diffusion features, and we call it diff. And then we can interpolate the feature map to get each point's specific point-wise feature vector. For example, get the embedding for the cat ear here. And finally, we just do simple feature matching with cosine similarity to get point-to-point correspondences for two images. Note that there's no extra training needed in the whole process. And here, given the source point on the left, we show the corresponding points on the right predicted by diff. And although simple, we can see that without any explicit supervision, diff can find pretty accurate correspondences on real images across instances and even image domains. For example, here, from a real photo to a sketch. This is actually an interactive collab demo. You can also play with your own images on our project page. And here are more of them. For example, cross-category from a duck to a bird or a penguin. And from a guitar to a violin. And here are galleries on more examples I just randomly selected from the internet. And we were all surprised by how accurate and robust the correspondences are, even from a real photo to abstract logo. For example, here, like the Statue of Liberty here. And we call such kind of correspondence as semantic correspondence. And we evaluated on two datasets, one of them containing over 12,000 test image pairs. And we compared to three types of baselines, including supervised ones that are directly trained with correspondence labels, weakly supervised methods, and also self-supervised features like Dino and Clip. And for diffusion models, we evaluate two variants, one trained on unlabeled ImageNet called ADM. So it's an apple-to-apple comparison with Dino because they all share exactly the same training data. And similarly, the other one is a popular stable diffusion trained on Lion as a comparison to OpenClip. And here are the bar plot comparison. And we can see diff outperforms both self-supervised and weakly supervised methods with a large margin, and even on par with the best supervised methods. And we can see the same trends on the other data set. And here, the diff even outperforms the best supervised method. And here are two randomly sampled cases. comparing Dino and Diff ADM, where Diff can find more accurate correspondences even given a large appearance changes. So here the task is to find the corresponding points on left to the right. And the same color denotes the same kind of points. And the red dot denotes a correct prediction, and the cross denotes a wrong prediction. And with the correspondences from Diff, we can easily propagate the edits from one image to others, even across domains. For example, here, an overlaid sticker. Or we can let all the birds to put up a bag. And with a smaller time step t, Diff can also do geometric correspondence. Here we show the match the key points given a challenging viewpoint or illumination changes between left and right. And here we show the homography estimation accuracy on each patches, which is one of the standard benchmark for evaluating geometric correspondence features. And we can see Diff outperforms the self-supervised features with a large margin, and even on par with the weakly supervised method CAPS. And Diff also demonstrates strong performance on temporal correspondence tasks, although never trained or fine-tuned on any video data. For example, tracking objects through video. More specifically, we can use Diff to propagate the segmentation mask from the first frame to the other frames of the video with simple feature matching techniques we mentioned earlier. And here are more results, like even for tracking multi-objects. Yeah, sorry, here I guess the FPS is really low because of Zoom sharing. But you can see, you can find more high FPS results on our project page. And here are the numerical results, and we can see Diff achieves strong performance. And even outperforms the methods that specifically trained on video data. And similarly, we can also do post-tracking, that is tracking the human joints through a video. Here are more results from a dataset on GHMDB, which is a dataset for human post-tracking. And the numerical evaluation, and we can see Diff even outperforms the methods that specifically trained on video data, which are the gray bar here. And through this project, personally, I really want to deliver a message that diffusion models are not just generative models. They are actually strong self-supervised learners that can understand the visual world. There are also a bunch of concurrent works showing the same argument by demonstrating pre-trained diffusion models can be used for segmentation and also recognition. One question I got asked a lot is that why correspondences emerges? This is a very tough question because in general, we still don't understand how certain things emerges from any large pre-trained models, ranging from ImageNet pre-trained feature extractor to Dino clip or even large language model nowadays. Here I just provide one of my intuition. Here I show the predicted clean image at certain time step during inference time. And we can see that at the beginning of the generation, that is larger time step, only a rough layout or object contour is being generated. And with the decrease of time steps, more and more details are being added. So that means different time steps actually focus on different levels of image understanding or image features. The larger time steps involves more semantic information, such that it can generate a rough bunny ear or eye, where smaller time steps involves more low-level details, such that it can generate the furry details of the bunny. And this cost-to-find generation process actually leads to a rich feature pyramid bank, and we can just choose different T to get different levels of features we want to do correspondence or some other tasks. And the other question is this surprising correspondence only happen within diffusion models? My answer would be probably not, because previous works also show that correspondence also emerges from other generative models like GANs. It's just not as accurate and as generalizable as diffusion model. I would say this is probably more like a property of generative models. And so far, diffusion model can fit the image distribution the best. For example, it's still non-trivial for GAN to fit the 5B lion nowadays, I guess. And the other question is this surprising correspondence only happen within diffusion models? My answer would be probably not, because previous works also show that correspondence also emerges from other generative models like GANs. It's just not as accurate and as generalizable as diffusion model. I would say this is probably more like a property of generative models. And so far, diffusion model can fit the image distribution the best. For example, still non-trivial for GAN to fit the 5B lion nowadays, I guess. And maybe this is even just a property of the visual world, because other self-supervised pre-trained features like DynoV2 also emerges pretty good correspondence. So as long as we can find a way to train a model on large-scale data in a scalable way, correspondence will probably eventually emerges. We can also draw such connection to the similar stuff happening in the large language model field. For example, the discussion on learning and compression. But for the sake of time, I will just stop the discussion here. And so in summary, we show that correspondence emerges from image diffusion models without supervision. And the resulting off-the-shelf diffusion features can benefit many tasks, including 3D segmentation and detection. And it can also be used to control image generation. For example, changing the rotation of the generated avatar here. And even for video generation and video editing. And meanwhile, I'm very excited to see more and more follow-up works on the intersection of diffusion models and image understanding, including key point detection, 3D scene understanding, and representation learning. Another piece I want to share is that it's actually to my surprise that after the release of our paper, the first few people reaching out to me are actually folks in the medical imaging field, where they have been bothered by the image registration and matching problem for quite a while. For example, how to draw the correspondence of these 2 points. Because naively applied optical flow or traditional like image matching methods won't work due to the domain gap, as well as the difficulty of obtaining annotation for medical scans. And our method actually showed a promising way to solve this problem in an unsupervised way. And I'm really looking forward to see the future of this direction. Okay, so that's pretty much the second part of the talk. I'll just pause for a bit in case you have any questions. So if not, I will just, yeah, go ahead, Chen.
Did anyone figure out how to systematically pick T and layers after we published the?
I think after that, people are more like, there are 2 types of works. Like first one, just use this feature. And second one, they just train like some other like sub-module to combine features from different layers. So in that way, you actually don't need to choose. You can have all these things, but it still comes to the question like you need a data set to optimize these parameters. So yeah, hope this answers your question. Yeah. Okay, thanks. So I'll dive into the last part of the talk. So given all the robust correspondence in image diffusion, could we enable more cool applications that were even not possible before? And that comes to our next project, RealView. So imagine the following scenario. You capture a perfect movement of your kid. However, you focus too much on their faces, but leave the other parts of the scene outside of camera frame. So the question is how to complete the scene. So given the rapid progress in generative AI, you decide to seek help from the state-of-art text-to-image models, where you could describe the scene using natural language as detailed as possible. And here are results from Photoshop Generative Fill and Stable Diffusion. However, you might find the scene doesn't look like as what you have in your memory. Unfortunately, you find you actually took a bunch of other photos of the same scene. Given these reference photos on the left, it's very easy for a human to hallucinate the original scene, that is filling the empty area in the target image on the right. So the question is how to let computer do the job. And that comes to our proposed algorithm RealView. And here are the final output on the right, where both the tricycle and the plush are recovered. So formally speaking, we are trying to solve such a problem. Given a few reference images on the left, how to fill a certain region of the target image, such that the output is feasible to the reference, and meanwhile, it's also a high-quality image by itself. This is really hard for geometry-based approaches. The main reason is that we have very few limitations on how the reference and target are captured. There could be viewpoint or lighting changes, or containing moving objects. And for example, here's the results of TransView, the state-of-art geometry-based methods. And this is definitely not what we want. And this is also hard for prompt-based approaches, as we've shown in the beginning, no matter how detailed the language prompt here, as shown here, it's still difficult to faithfully recover the details as in the reference. As shown here, like the dresses are all beautiful, but just not the same dress. And in order to solve such problem, we are trying to seek help from generative models again, who already have a really good image prior. Intuitively, we first insert the knowledge of the scene into the model, such that to make it aware of the scene contents in the reference and target images. Then we can use the adapted generative model to generate the empty region. And as you can see here, here's the output of our model. The background is still gray, it's black and white, and also the dress is colorful and the same dress as we shown earlier. So more specifically speaking, we use LoRa to fine-tune the pre-trained stable diffusion imprinting model on both the reference images and target images. So given a training image, we generate a random mask and apply on it to get a masked image. Then we add random noise to the input image to get a noisy version. Then feed them and the language prompt with a fixed rare token V into a pre-trained text-to-image imprinting diffusion model. And in order to preserve the pre-training prior, we fix all the weights and add low-rank matrix to them, which is a common practice for fine-tuning large pre-trained models nowadays. And then we calculate the reconstruction loss and use it to fine-tune the LoRa weights. After the training is finished, we can just use a fine-tuned diffusion model to imprint inference, to do imprinting inference just as usual.
Wait,
So you go back.
here there's only one image, but you have a set of images.
Yes.
How are you going to do that?
Oh, this is like I mentioned, you are training on multiple images in a batch manner. So this is just one of them. You also have a few other images. I mean, you can also only train on one image, but with different
But
augmentation.
during test time, what you have is you have some reference image and one image that is like only
I see.
part of the information. How do you
Yes.
combine reference and
Oh yeah, like I mentioned, so here's the training stage. Like after the training is finished, you can just use this fine-tuned model to do imprinting inference as usual. It's kind of like a customized model on this thing.
how do you add these sort of reference information into your model?
Oh, because the model is fine-tuned on these reference images.
So it's per scene
So
or
Yeah, it's like a per scene optimization.
Proceed.
Yes.
Okay, then never mind.
Yes.
Okay, cool.
Cool. Yeah.
Okay. So when you're doing this,
Mhm.
right? So if I understand correctly, so this is a text to image
Yes.
diffusion in painting model. So this
Yes.
is a specialized model for in painting,
Yes, it's actually a model fine-tuned from original stable diffusion.
and
Yes.
it takes three inputs: a noisy image, a mask, and
Yes.
a masked image.
Yes, actually these three things are concact together, like so the channel is really,
Okay.
yeah.
Okay.
Okay, so here let me show you more results on real view. It's able to handle dynamic scene. For example, filling the crown of this dancing girl here. And it can also handle large aperture changes between reference and target. For example, the elephant logo on the wall is recovered, but also stays blurry due to the large aperture. However, the left images are captured using my own iPhone, so you can see the aperture is actually really small. It can also handle large lighting changes between reference and target. For example, the same place but captured in day and night respectively. Okay, I see like the FPS is really low here. It can also handle the difference of image style between reference and target. For example, recover the beautiful Queensboro Bridge in New York City in an old movie by Woody Allen.
That's one question. So, for this case, your training is only the reference images.
Actually, we also train on the how do I say, like the target image, but put in the empty mask.
Okay.
Because there are still some information in the target image.
So
When
you
we
pick up all this, and then do
Yes.
inference. What you do is you feed in the target image, let it in paint.
Yes, exactly.
Okay.
So you can view it as a kind of nerve, optimize on these images.
Sure.
Okay, and the next, sorry, stop moving. And by treating other frames of a video as reference images, we can also use real field to uncrop the close-up shots of TV shows. For example, the famous turkey scene in France. And in addition to outpainting, real field can also do inpainting. For example, remove the construction cover for a landmark. And besides removing things, real field can also insert objects into the scene. Even the reference and target photos are captured from different viewpoints. For example, the White House here and the cat feeder here. And it's also able to remove the foreground objects, like the cup here, but while maintaining the defocus blurry effects behind it. And in addition to all these qualitative results, in order to quantitatively evaluate how well our method performs, we collected a data set called RealBench, and it consists of 33 diverse challenging things with viewpoint, lighting, aperture changes, moving objects, covering indoor and outdoor impending and outpainting scenarios. Here's one example from the data set. Given the reference image on the left, we aim to fill the image on the right. And here we show the reference, ground truth, and our results side by side. For better visualization, the existing area is covered by a transparent wet mask. So the area outside the mask is the generated region. And as you can see, although the viewpoint changes a lot and people are moving in the scene, our approach still gives very similar results as the ground truth. And we compare real field to two types of baselines, including the prompt-based baseline like Stable Diffusion in painting, and the Photoshop generated field, which is a commercial level in painting method, and the reference image-based baseline, including paint by example and transview. And here are the results side by side, and we can see real field gives the most faithful and high-quality results. And here are more comparisons. This is actually a image took by myself in my sofa in my living room, and yeah, we can see like our results gives very similar results to the ground truth compared to the baselines. Like generative field would give you a good results, but just not the same thing, no matter how detailed language prompt is. And here is another example. Our method is able to recover the robot, and transview the geometry-based approaches feels catastrophically because people is moving. So it's really hard for it to understand what part should be moving and what part it's not moving because it doesn't have an image priority. And generative field will give you a good robot, but it's not the same robot. And in order to do quantitative evaluation, we calculate the similarity of model outputs versus the ground truth images. We consider the following metrics, including low-level similarities, including PSNR, SSM, and LPIPs, and they are only calculated on the field region. And we also consider the high-level similarities like Dino and Clip, and also mid-level similarity called DreamSim, a recently proposed distance that focus more on image layout, object poses, and semantic content. And here are the results. We can see real field outperforms baselines with a large margin. It should be noted that although transview, the geometry-based method achieves a decent number on low-level similarities like PSNR, but the output completed image is usually quite low quality due to the lack of a good image prior, as we showed earlier, especially when the scene structure has complex depth variance beyond a planar surface, which is really hard for homography transformation to approximate. And in addition to quantitative evaluation, we also conduct user study on 58 challenging scenes, comparing real field versus baselines in terms of realism and physicalness. Specifically, participants first review an incomplete image, target image, alongside with the outputs of 4 different methods, choosing the one they found the most realistic. Then, with these reference images provided on the left, they are asked to select the most faithful completion. And we collect the results from 44 users, so over 2,000 votes per criterion in total. And we can see real field significantly surpasses baselines, especially on the faithfulness criteria. And so a natural question is why real field could work. And we give the following 3 hypotheses. First, we hypotheses actually have an implicit 3D understanding of the scene. Here's one scene from NERF, the hot dog scene. We train the model on 100 training views, and then we evaluate its impending results for the test views and compose it into a video. Here, just like the visualization before, the existing pixels are washed out. So the center of the video is actually the model output. And we can see, although there's no internal 3D representation and each frame is generated independently, the results are pretty multi-view consistent. And here's another forward-facing thing from NERF. And the model is only fine-tuned on 5 training views, which is a few-shot null-view synthesis setup. And we can clearly see that the model is doing some 3D adjustment internally. If you are seeing the high FPS video, I'm not sure you can feel it through this low FPS. Secondly, we hypothesize it has a compositional understanding of the scene implicitly. So during inference, instead of conditioning the generation on the target image, we can make the fine-tuned model actually conditioned on an empty image, empty canvas, which means that the model is just imprinting the empty canvas. And interestingly, it will generate something very interesting, like generate multiple scene variants with different structures. For example, manipulating the object layouts, like inserting another kid in the middle or remove the kid from it. Or remove the foreground or background object, like remove the person one by one here. And this suggests that RealField is able to relate the elements inside the scene in a compositional way. And the last hypothesis we make is actually similar to our previous part. Like RealField captures correspondences among input images. So even when the reference images and target images on the bottom does not describe the same scene, the fine-tuned model is still able to fuse the corresponding contents of the reference image into the target area seamlessly. For example, attaching my cat, this is actually my cat called Koala Cup, attaching my cat head into the body of the famous Dream Boost dog. So here the dog is actually not used. I'm just put here for reference. So lastly, we also want to talk about the limitation of our work. Firstly, it's definitely not real time due to the need of fine-tuning. And secondly, we can also find that when there's a large viewpoint change between reference and target, RealField fails to recover the 3D scene faithfully, especially when there's only one reference image. For example, here, the reference image is captured from a side view, and the target is from a center view. Although the results looks plausible, but if you look closely, the pose of the husky is actually different from the reference. And lastly, because RealField actually relies on the base pre-trained models image per hour, it also fails to handle cases that are also challenging for the base model. For example, we all know Stable Diffusion is not good at generating fine details such as text, human faces, or body parts. And here, the text on the store sign looks plausible, but if you look closely, it's actually wrongly spelled. So in summary, with only a few reference images, our proposed RealField can input and output the target image with contents that should have been there instead of what could have been there. And the success of RealField actually shows that the fine-tuned diffusion imprinting model is a strong in-context learner, in the sense that it understands the image contents, and we just need to find a way to prompt the information out. For our case, it's image completion. And the recent work is doing very similar stuff, but for lighting query. And I'm looking forward to seeing more future works along this line. For example, going one step further, how to query the depths or even 3D geometry of the scene. Lastly, I will briefly talk about a few future directions I have been thinking on. One orthogonal direction I've been fascinated with is video. My previous work is mainly focused on static images or 3D, but the actual world is dynamic. Although this is a hot field, but looks like we're still far away from achieving realistic results. For example, here, left is the runway video generation results from a soccer game, and read it the real one from Leo Messi. So one interesting question to ask is skill enough in terms of both data and model that all we need to transform from left to right? For example, the recent Sora from OpenAI. Or do we need more human or physics prior to explicitly or implicitly model the thing and objects, just like the stuff we are doing in 3D or graphics? I asked many people this question, and looks like people are having different opinions. But in whichever case, I think video generation is very cool. It will also impact video understanding, just like the stuff I showed earlier, but on the 2D image cases. And another direction I'm interested in is to unify visual understanding and generation. So generative pre-training has proven highly successful in NLP, unifying various downstream applications. However, in computer vision, understanding and generation are still approached differently. Recent works show that image generation models like diffusion models can learn like pretty good image representation, rich in semantic information. However, this model still lag behind contrastive learning models like DynoV2 in general video understanding capabilities. Conversely, well, autoregressive modeling with transformer architecture prevails in large multimodal models like Lava or something. It significantly underperforms diffusion models in image generation quality. Therefore, determining the best model to unify visual understanding and generation remains an open problem. And that's pretty much all of my talk today. I will leave the QA to the end. But thanks for attending, and I will be really happy and also flattered if you find any piece of the talk interesting or inspiring. And okay, so finally it comes to the most important part of the talk, acknowledgements. First of all, I want to say a big thank you to my advisor, Bharat, for his unconditional support and guidance over the past 5 years, especially for taking a rotation student with leap of faith. I'm incredibly fortunate to work with such a brilliant, kind, and humble professor who will always serve as a role model in my life. I'm especially grateful for his patience and freedom he granted me during my darkest moment of the pandemic. He maintains a childlike curiosity for computer vision and consistently encouraged me to find my true passion and work on important, valuable problems that are overlooked by the field. And lastly, his relaxed personality and unique sense of humor have always made my PhD journey much easier, because our one-on-one meetings are always filled with joy and love. I would also like to thank Noah and Steve for serving as my committee members and for their insightful suggestions and discussions. I'm pretty regretful that I didn't cherish the time with them, such that I'm still bad at graphics and 3D vision now. I also want to thank my industry mentors, including Zhongyi and Mingyu at NVIDIA, and Nathaniel, Neil, and Mickey at Google. Thanks for bringing me to 2 great research teams and the chance to work on impactful projects with all the amazing researchers. My whole thesis would not be possible with all the great collaborators and lab mates at Cornell, NVIDIA, and Google. I'm so fortunate to work with them and also learn so much from them on brainstorming research ideas, conducting experiments, and writing papers. I always enjoy the insightful discussions with each of them, and always miss the days when we rush deadlines together in the midnight. And due to the space limit, I cannot put all the pictures here. So sorry if you didn't see yourself in here. I also want to thank all the good friends I met at Cornell, especially Pauls from the soccer club, for providing me with a warm and supportive community and letting me enjoy my life outside research. I also owe a big thank you to my parents. Although we haven't met in person for over 5 years, that's the reason why the photo is here is actually taken during my undergrad graduation. And they also know very little about research, but they always give me the best unconditional love and support. And lastly, I want to extend my gratitude to my girlfriend Zia and our cats, Shibao and Shimei. Thank you for always being here through the whole journey, and looking forward to the new chapter of our life adventure in New York City. Okay, so what a ride. Thanks for coming again, and feel free to let me know if you have any questions.
So I didn't do a logistics spiel before the talk, but I'll do it now. So now that the talk is over, the next phase is public Q&A. So anyone can ask questions. After that, we will have a private session where it will be any faculty members and Luming, and then there'll be a final deliberation. So yeah, this is the public phase. Anyone can ask questions.
May I ask a question from?
Yeah.
Sorry.
Go ahead.
From online.
Hi, Yuanxi.
Very excellent thesis defense with really amazing result. I'm curious about the visual correspondence part. How do you extract the pixel locations? Would you like to give some details? Because it's
yeah, that's a good question. So as I mentioned, our method is actually just a feature representation. So we are not responsible for the feature detection part, like key point detection part. So the key point is actually either pointed by human or extracted using other key point detection method like SIFT or superpoint.
Oh, so you need to locate a feature vector that defines the pixel location, and then you use it to run a matcher to find whatever vector image.
Oh no. I thought you were referring to another example. But for example, for the example here, is the video still playing or no? Okay, it's playing now. Like you just click the image point on the left, and we'll find the corresponding points on the right because it's matches. Try to compare the cosine similarities with all the points on the target image and output the one with the largest cosine similarity.
All right, thanks.
I'm not sure this answers your question or not. But for example, for the geometric one, the key points here are actually calculated first extracted using SIFT. And then we just do the matching. Yes.
Yeah, thank you.
Go ahead.
I'm also interested in this work, and you see that we don't actually need to have the actual geometry constructed. How do you see this kind of model being benefit from having the geometry, or we don't actually need the geometry for any of it?
That's a good question. So if I understand correctly, you just mean that given the great power of the diffusion model, do we still need geometry representation at all?
Yeah,
I think that's a good question. I think we still need that because if you truly want to manipulate an object in 3D, geometry representation is probably still the best way to manipulate it. And our method just provided a way for you to find the correspondences between images such that you can probably better reconstruct the geometry. I think it's two different stages of the pipeline, I guess. If I understand your question correctly. Yeah, go ahead.
My question is on real field. One thing, so one thing that you mentioned is the limitation is it's not real time, right? Where do you see what would be the sort of next step towards fixing this issue?
That's a good question. I think the best way to fix this is just add an additional conditioning on reference image in this pipeline, but in a feed-forward way. This means you first construct a data set with image pairs, and then you randomly select some reference images and condition on them. Let the model to condition on them using attention layers or cross attention, or even just simply concatenate them together and train this model to do conditioning generation. So it's very similar to the genes project on the seminar. But I think the limitation of that is first of all, how do you get this data set? Because it's not very easy to get a diverse data set with diverse scenarios, different, the same thing, but different lighting, different viewpoint, different aperture, different camera. So yeah, I guess that's the main difficulty. But probably video is a good source. Actually, we were discussing about this direction at Google because the product team is really interested in this because it seems like a very useful feature for Pixel. But definitely, doing online optimization is not good.
Yeah. So I guess one question I have, I have this. So you have this diffusion model just trained on all this like natural images.
Mm-hmm.
And then for the conditioning model, what you said is very difficult to collect data.
Yes.
What if you use sort of synthetic data for like training the conditioning mechanism?
Yes.
And because you have this diffusion model that's trained on natural images, do you see like using like prior from natural image
Yes.
data from synthetic data would actually give you what you want?
Yeah, I think that's a reasonable direction. Like you just fine-tune the prediction model, add additional attention layers to fine-tune on the synthetic data set where you have more data. I think that's a good approach. But one question is like, how do you like collect such synthetic? Like you mean from graphics engines, like game engines?
Yeah, why not?
Yeah, I think that's reasonable. Thanks for sharing. Yeah.
I have a sort of a related question there, here, right? So if you take this, so in this real field work, you have a set of reference images. You want to extract the outpaint a target image, right? Now, if I consider, for example, what Gene was doing, which is sort of now do synthesis, and there sort of you're not conditioning on, you're not outpainting, but rather you are conditioning on camera pose.
Yes.
Right. Do you think one could do something? Do you think it would still help in that kind of a setting to sort of fine tune the model on the scene, particular scene, like a scene specific model?
That's a good question. Yeah, I think it probably would. Yeah, I don't know, but Gene's work also trained on diverse data set already, right? Like on the conditional camera.
This one, right? I mean, like the in-painting model is trained.
I see. So you mean after get the general model, we can still do per scene optimization?
Yeah. Would that help?
Yeah, I think that makes sense. I always feel like this kind of how do I say, conditioning masked prediction would always help, because it will enforce the model to understand, to compress the information of the scene based on the 2D images. So I think it probably would, yeah. We just need to find the correct objective, I guess. Yeah.
Sounds good.
Cool. Thanks. Yeah, I think it's a reasonable direction. Yeah.
Any more questions?
Yeah, I have one. So, hey, Luming.
Oh, hey, there it is. I know, see, yeah.
Hey, well, Cornell. So I have a question on DIFT. So you said that the way that you're doing it is you're interpolating between feature locations in a given feature map on one of the layers of your underlying base model, and you indicated that the choice of layer is important.
Yes.
So what happens when you pick the wrong one? Are there any general trends that you've observed?
Yeah. I mean, that's a good question. So there's actually adaptation study in our paper. Like we show how the performance varies with different layers and different time step t. And usually the layer, like I mentioned here, we actually didn't dive into like very fine-grained layers. We actually are just using like a very close search on the blocks. And there are only like 4 blocks. And usually the first one and last one is really bad. So usually you just choose between the middle 2. So it's not that much hard work. So what I would suggest is like for a specific task, you just try the parameters and see how the performance works. And usually these choices will be pretty significant. Like for example, for semantic, we use like the second layer. If you use a third layer, a third block, results will decrease like significantly.
Interesting.
So, but yeah, this is like hyperparameter you need to turn, I guess. Yeah.
So you probably couldn't just sort of take an average of all of the outputs and see what that's like?
I actually did that, but I found that the performance will actually decrease compared to the best parameter. But the other way is just like I mentioned in the middle of the talk, is like you train another network to fuse all the features together. That probably would help, but it also comes to the question like you need to collect the data first.
Yeah.
Cool. Thanks.
Cool. Thank you.
All right. I guess I will ask all non-faculty members to leave. with the exception of null, of course.
Okay. What was the stop recording?